Hello everyone, welcome back to Untitled Engineering. We are still on Applied Thermodynamics, Power Mechanics and 6. We are already familiar with the structure that it's on our screen, that it's the steam plant. And we know that there is a large amount of heat energy escaping the combustion chamber with the fuel gases as they are coming out of the combustion chamber. And the reason why we pass the fuel gases through the superheater, the economizer and the air heater before we release them to the atmosphere, it is because we want to recover most of the heat energy that is coming out of the combustion chamber with the fuel gases. Now, to calculate the heat energy that was not recovered in these three components, which will be the heat energy that was lost with the fuel gases, we are going to calculate for the heat energy at the chimney base and calculate the heat energy at the atmosphere, or the heat energy of the fuel gas after being released to the atmosphere. And then that difference, that is what we are going to say it's the heat energy that went out with the fuel gases. So the heat gases, the fuel gases are divided into two. We have what we call dry gases. Dry gases, it's the smoke that you see being released to the atmosphere from the chimney. And then we have wet gases. Wet gases develop when there is hydrogen in the combustion chamber. And the only way we can have hydrogen in the combustion chamber is if the fuel that we are using has hydrogen as one of its ingredients. We know that hydrogen, when it reacts with oxygen, the product that we are going to get is H2O. We know this from combustion of fuel, Power Mechanics and 5. So this water, it's now in the combustion chamber. The water will absorb the heat energy that is in the combustion chamber, which will convert it into superheated steam, which will later escape the system or the steam plant with that heat energy. And we are going to say that heat energy was lost since it was not used in the evaporator. So to get the total heat energy that was lost with the fuel gases, we have to get the heat energy that went out with the dry gases and the heat energy that went out with the wet gases. For us to calculate the heat energy that went out with the dry gases, we're going to use this formula. Let me use another paper. We're going to use the formula that says the heat energy that went out with the dry gases, it's equals to specific heat mass of dry gases times specific heat capacity times the temperature at the chimney base minus the mass of the dry gases times the specific heat capacity times the atmospheric temperature. The mass and the specific heat capacity, they are the same. We're going to take them as common, which will give us a formula that says mg times the specific heat capacity in bracket the temperature at the chimney base minus the atmospheric temperature. This is the formula that we're going to use to calculate for the heat energy that went out with the dry gases. This is the heat energy at the chimney base, and this is the heat energy of the gas after being released to the atmosphere. And then to calculate for the heat energy that went out with the wet gases, we're going to say Q wet is equals to the enthalpy of that steam at the chimney base minus the enthalpy of that steam after it has been released to the atmosphere, which will be, this one will be mass times, let's say we are having superheated steam at the chimney base, will be H sup, but this, they can even tell you that it's not superheated steam, it's wet steam. So it will depend on the condition that they give you. In this example, we are going to use it as superheated steam, and the heat energy of the water after it has been released to the atmosphere, we are going to calculate using m of water times specific heat capacity of water times the temperature or the atmospheric temperature. And then this and this are the same. We take them as common. We're going to have H at the chimney base minus the specific heat capacity times the temperature, the atmospheric temperature. And this is the formula that we are going to use to calculate for the heat energy that went out with the wet steam or the wet gases. And then coming back to the fuel gases, the mass of the fuel gases, the total mass of the fuel gases, we are going to get using the air fuel ratio. Air fuel ratio. We know air fuel ratio, it's given by, let's say in this case, they tell us that it is 9:1. And this tells us that for every 1 kg of fuel entering the combustion chamber, it will come with it 9 kg of air, which means this will be 9 plus 1, giving us the total mass that is in the combustion chamber as 10 kg. This will be the mass of the fuel gases, the total mass of the fuel gases that are in the combustion chamber. And the mass of the fuel gases, it's equals to the mass of the dry gases plus the mass of the wet gases. And then we have what we call a heat balance sheet. Let me write it here. A heat balance sheet. A heat balance sheet, it's a diagram which we draw to navigate how the heat energy that is produced by the fuel was used. In the first column, we are going to have heat value, which is the total amount of energy that is produced by the coal. Let's say it's 10 kilojoules. And then here we're having distribution. This is how it was distributed. We are going to start with the heat energy that was transferred to the steam or to the feed water in converting it to steam. The heat energy that went out with the dry gases. The heat energy that went out with the wet gases. And then let's say the heat energy that went out, that was transferred to the steam is 7 kilojoules rather. This is heat energy in kilojoules. And then let's say the heat energy that was transferred to, that went out with the dry gases is 1.5. And the heat energy that went out with the wet gases is 0.5. It's kilojoules. When you add this, 7 plus 1.5 plus 0.5, this will give you 9 kilojoules. But the total amount of heat energy that was produced by the coal is 10 kilojoules. Therefore, we're going to say 10 minus 9, and we get that it is 1 kilojoules. This 1 kilojoule, it's what we are going to say, it's the heat energy that it's unaccounted for. It's heat energy unaccounted for. This might be the heat energy that was lost due to incomplete combustion of the fuel that we are using. And then from here, we are having percentage. Now we want to express this in percentage form. We are going to say 7 divided by the total amount that is expected from the fuel according to the heat value times 100. This will give us 70%. This will give us 15%. This 5%. And this will give us 10%. And this is the heat balance sheet. And that is how we go about drawing the heat balance sheet. Here we are going to have total. This should be, the total of this column should be 10 kg. This is 100. We know percent it's 100. And that is how we go about drawing the heat balance sheet. And that is the end of our lesson today. I will see you on the next lesson.